We have a really exciting panel in front of us. So if there is one method where really the state of the art has changed or is changing over the last 2 years, it's the difference in differences. And we are really fortunate to have today some panelists who are really contributing to the progress in terms of where this method is going and how we should think about this type of inference. And so all the glory goes to Evan, who's organized the panel. Thank you very much, Evan. And we're really happy to welcome Andrea and Jonathan today. So Evan, do you want to make a short introduction, and then I'll do a little bit of advertising for the 4th edition of the Meta method.
Sure. Thank you, Tomas, for having me. And I'm happy to take the credit. It's totally undeserved. The credit really goes to Andrew Goodman-Bacon and John Roth and several of their contributors who have pushed our understanding of what can go wrong in differences and what we can do about it. And so that's really what today's feature is about. So let me introduce our two panelists very briefly. Andrew Goodman-Bacon, who just goes by Bacon, is an economist at the Opportunity and Inclusive Growth Institute at the Federal Reserve Bank in Minneapolis. He's formerly an assistant professor at Vanderbilt. Andrew's research is on economic history, health economics, public economics, and applied econometrics. Fun fact about Andrew, or Bacon, I should say, Bacon and I started in graduate school together. We were in the same study group in our first years. And I remember Bacon working on this diff and diff stuff in 3rd year or 4th year. And the final work was finally published about a decade later. So Andrew is a testament to his persistence here, that he was really ahead of the curve of all of this stuff. John Roth is an assistant professor in the economics department at Brown University. He's interested in econometrics with a focus on causal inference. He was also a senior researcher in the office of the chief economist at Microsoft. And John has been doing some amazing work thinking about pre-trends and contributing greatly to this literature on diff and diff. So, so thrilled to have both of you guys here. Welcome to everybody else. Tomas, let me hand it back to you to do a little advertising, and then we'll go straight to Bacon.
All right, perfect. Thank you, Evan, and thank you again, all. So just in terms of a little bit of advertising, we have an upcoming Meta Method panel, number 4. It's slightly different because it's not going to be focused on one particular method, but something that we feel, and also as we've run the survey with all the STR members, something that came actually at the very top in terms of your interest was this idea of how do you achieve and how in a sense, what are the best ways to think about the theory empirics fit? And we're going to have 3, again, great panelists, Maggie Zhu, David Tan, and Gurnetta Singh. All 3 of them are editors at different top journals in our field. So they'll give us an editor's view of how to best achieve and how to deal with some of the issues when you're striving for the fit between your theory and then both empirical design and measurement. And with that, I'm going to stop sharing my slides and hand it over back so that we can start the panel.
Okay, so in terms of structure, what we'll do is we'll start with Bacon, who's going to go for about 35 minutes or so. Feel free to put questions or clarifying questions in the chat, and then we'll hand it over to John, and hopefully we'll have some time for Q&A at the end. So please do ask those questions. So let me hand it off here to Andrew Goodman-Bacon.
All right, great. Thanks so much. I'm happy to be here. I really like talking about this. And I should also just right now get out of the way the fact that to the extent that the Federal Reserve System has opinions about differences, the things that I'm about to say are not those opinions. So I'm gonna talk to you guys today about what happens in a differences model with staggered timing. So I'm sort of jumping a couple steps ahead, and I'll just tell you what I'm going to conclude and try to convey, and then we'll walk back and kind of march up to that conclusion today. So what I mean by staggered timing is that you care about a policy or you care about some phenomenon, the effect of hurricanes on infant health, or the effect of like mergers on prices, or the effect of some public policy on mortality rates. And those things happen at different times for different units. Policies don't turn on in all states at the same time. Sometimes they do, but usually they don't. Mergers don't happen in markets at the same time. Hurricanes don't strike at the same moment all the time. A lot of things. I mean, it takes some kind of special circumstances for a treatment that we really care about to just strike at one moment. I'm going to tell you today about some of the challenges about using regressions to understand the causal effects of policies that act like that, or treatments that roll out in that way. And basically the two things that I want you to leave with are that staggered timing variation. It can still be okay. It's not, I don't think any of the new developments in this literature are saying that staggered timing itself is not useful. It can be really useful. And so it can be okay to identify treatment effects. But the main conclusion from my space in this new literature is that regressions are not often very good for estimating these things. There are ways to kind of trick regressions into working a little better, but I don't usually like to think of them that way. I sort of like to think about other ways to construct comparisons, sometimes kind of by hand rather than just hitting reg in Stata, that are clearer about what's going on and sidestep a lot of the issues that can arise when you use a regression. So now we get to walk back a couple steps and say, just at the most basic level, what is difference in differences? I sadly in half an hour don't have time to talk about all of the public health epidemiology history of this type of method, but the basic idea is that you are going to compare, instead of comparing two groups, one of whom is treated and one of whom is not treated, where that comparison can go wrong for all sorts of reasons. If you would have said outcomes are higher among this group of neighborhoods than this group of neighborhoods, or this group of firms than this group of firms. We social scientists have tons of reasons why we can cast doubt on those kind of comparisons. They could be due to all sorts of things. The idea of diff and diff is say, well, what if we observed all those same units, those same people, workers, firms, states, counties, whatever. What if we observed them before the treatment that we care about actually even took effect? Presumably, hopefully, many of the things that make them fundamentally different and incomparable to each other would still be there. And the only thing that would differ would be the presence or the lack of the treatment that we're interested in. So the idea of difference and differences is that you compare the difference in outcomes over time for units that become treated to units that don't become treated. So that's difference one, is like what happens before and after treatment, between the group that actually does get the treatment and the group that doesn't. That's difference two, treatment versus control. So the simplest way that people will talk about it, or I might mention it, is like pre-post treat control. Those are the two difference, and that's why it's called difference in differences. So in this graph, you'd be comparing, obviously this is a contrived little picture here, but you would compare the average outcomes for these black triangles in the post period, that's after, T star K, to the level in the pre-period, that's before T star K. And that would be the change in outcomes for the treatment group. And you would compare them to the change in outcomes for the untreated group, this gray line right here. And that would tell you, under some assumptions, that difference in means right there compared to this difference in means right there, that would tell you the treatment effect, a causal effect of the policy that went into place at this particular time. So here's other ways to write this down in terms of means. So we'll come back to, this is kind of an important way to express what a difference in differences estimate is, because this is looking at things in terms of just means in the data instead of like regression coefficients is a pretty key ingredient of thinking through some of the new developments and how we can estimate these things. So I want to just linger on this for one moment. You can, to write these means, you could say the Y bar treat post, that's going to be the average of the outcome in the treatment group, that's the black triangles, in the post period, that's to the right of the red line, minus the average outcome in the treatment group in the pre-period to the left of the red line. So that's these two green dashed lines. And then here's the same thing for controls. The thing, so we'll skip that for a second. So that's another way to write what a simple difference in differences estimate is. So when I say simple, I mean like you have some groups that get the treatment, some units that get the treatment, some that don't. This is often how this method was developed. That's the nature of the earliest diff and diff estimates that come from these like historical epidemiological approaches. There's some famous papers on minimum wages where the groups are, a state that changed its minimum wage versus a neighboring state that didn't. Those are the treatment and control groups. And before and after the minimum wage change is pre and post. I'm going to hold off on this for a second and just say that the link that I'm really going to focus on today is when you have a simple setup like this, you can get this exact same number, this exact difference in means, this nice kind of, to me, very intuitive thing, because it comes from just averages in the data. Like I can calculate it by hand. I know what an average is. That's nice. I like that. You can get that exact number by running a regression, which is also very convenient. If you run a regression of outcomes, Y for units I in time periods T, on a dummy for the treatment units and a dummy for the post period, the coefficient on an interaction term between the treatment dummy and the post dummy, that literally that algebraically equals that difference in means. Okay, so this is great. Like this is a really nice connection, because regressions spit out standard errors. You can adjust the standard errors in different ways. It's pretty simple, and it's a nice connection to know exactly where your regression coefficient comes from in terms of like averages in the data. That's something I really like. I understand it a lot better. I think it's easier to explain. It's a very elegant link here in the simple diff and diff case. So I'm going to motivate a lot of what I'm going to say using this example of how did the Affordable Care Act's Medicaid expansion affect insurance coverage. So if you don't recall, the Patient Protection and Affordable Care Act was passed in 2010, and it originally mandated that all states should expand Medicaid coverage, so public health insurance, for childless adults up to 138% of the poverty line. And that was new in a lot of states. Many states didn't cover up to that level. Then there was a Supreme Court case in 2012 that said, no, this cannot be mandatory. States can choose. And so this created this great diff and diff situation where some states really did choose to cover a lot more people under Medicaid, and some states chose not to. And so I think there were lots and lots of health policy researchers and health economists and other social scientists who were just like ready. They had the data coded up so that as soon as they got data from the Current Population Survey or the American Community Survey in 2014, when these expansions took place, they could do exactly what you see on this graph, which is say, calculate the health insurance, the share of people with health insurance among adults in states that expanded Medicaid in 2014 and states that didn't. And they would have produced this picture, in summer of 2014 or something like that, 2015, when these data came out, they would have produced this picture and been incredibly happy, because these two states have a little bit different levels all throughout 2008 to 2013, a little bit higher insurance rate among the expansion states. These are primarily they're more northern, they're more democratic states. And then you see a little bit of a divergence. As soon as the Medicaid policy changes, the change in insurance is a little higher among the expansion states than among the non-expansion states. And this fits exactly into the simple diff and diff, what I call this 2x2 treat control pre-post diff and diff that people understood. So life was simple when this was true, right? The diff and diff treatment effect here says that Medicaid expansion increases health insurance by 5 percentage points. That's great. Nice looking picture, compelling number, easy to calculate. This is great. So then time moves on, and some other states decide to expand. So not all states did it right away. So then now you get to 2015, and a handful of other states said, well, we didn't want to do it right away, but now we're ready to pull the trigger on this expansion. Let's do it. And so now you're left with this question like, well, what am I supposed to do now? I mean, you could still compare the 2014 expanders to the non-expanders, but you got this other group. They also did it, but they didn't do it right away. And so the question, I think, with this kind of setup, now the treatment as time moves on starts to be staggered instead of just one and done, really. And it gets even more confusing. Like if you go on today, there's lots of other groups of expanders. Some states did it in 2019, for example. And so you have all these lines, but I think the challenge for researchers to say, well, there's a lot of information in here, right? Like there's a lot of comparisons. There's a lot of different times when some state has the policy and some state doesn't. How are we supposed to extract like a causal number from this? Like what really was a measure of the causal effect of the ACA Medicaid expansion on health insurance. And the traditional way that I think people have been doing this, have been approaching this, is to just run a more flexible regression. So I think that the logic is kind of, the intellectual history here was to start from this fact that You could do a simple diff and diff in that sort of original case by hand, and that was nice and it was clear. You could show it in a table. That was the same as the regression estimate with the treatment dummy, the post dummy, and the interaction of treat and post. And so then you said, well, if you have a more complicated setup, why don't we just expand the regression specification? So instead of a treatment dummy, why don't we just put in fixed effects for every single unit? I mean, how could that be worse, right? It's more flexible. Instead of just one dummy for a group of units, we'll have dummies for every unit. Instead of a post dummy, why don't we have dummies for every time period? I mean, again, I think the logic was this, how could this be worse? It's more flexible. And then when you put those numbers in, or those fixed effects in, then you can just put in a treatment dummy that does whatever. It could be continuous, it could be changing over time. This kind of taking this from a more explicit diff and diff context into a more kind of like panel type regression framework. But the good thing about this is that it ran. It would give you a number. And you kind of had an idea of what, people had an idea of what these numbers were, but we weren't very precise about this. And so that's basically what my paper does. And that's what I'm going to explain in the next couple of minutes. Because at least for me, primarily a practitioner, really breaking apart this regression coefficient and understanding like what's in it, how it's formed, and how that can become either problematic or at least weird in terms of interpretation has been really, really helpful. And if I didn't sort of have my head around the problems, I don't think I would be able to fully comprehend like what the new proposed solutions are, which are really related to like the form of the problems, I think. So that's, I'm gonna dive into now like what my paper says, which is exactly what you see on the screen, beta hat DD. My paper is just about breaking that coefficient up and saying what it is and understanding what it is. And then there's lots of other new work by John, by Pedro Santana, by Brant Calloway, by Kirill Borusiak, by all these people. Tons of people are in this space now saying, what should you do instead of this? And I think that, like I said, the understanding the solutions for me has required like a pretty deep understanding of what the problems really are. So my main tool for dealing with this is just doing a bunch of algebra. So when I look at fixed effects in regression, I start thinking about fixed effects are soaking up means. Okay, so taking out the unit means here by like the Frisch-Lavelle theorem, which is one of my favorite theorems of all time. I use it all the time. All you have to do is kind of take out the variation of your covariates from your key right-hand side variable. So that's what I'm doing. I'm going to say, well, we don't want to compare average differences in treatment across units. So we're going to take out the mean of D, the mean of the treatment dummy for each unit I. And then we'll soak up the time variation. We'll soak up the time dummies. We're going to take out the average of this variable over time. Now, these details don't matter. I just wanted to say like how the starting point of all the algebra I did, which I'm about to skip. What the Frisch-Lavelle theorem says is basically once you soak up these means and you adjust your key treatment variable, you take these means out of it, then all you need to do is a univariate regression of your outcome on this like adjusted treatment variable. And this expression down here, which you don't need to linger on, is the thing that I dive into and I break up and I work through the algebra of what that thing actually really equals. But I'll explain it to you in a more, explain how we get there in a more intuitive way. So let's think of like a more kind of simplified example from the ACA. And imagine there really are only just 3 groups of states in the whole world. There's non-expansion states that never do this policy as of 2019. There's early expanders. Those are the 2014 states that like jumped right on it. And then there's 2019 expanders that waited 5 years and they did it late. Imagine those are the only 3 groups in the world. And this is what your plot would look like. If you had the data in your computer, you knew which cohort different groups of states were in, like when they were treated or if they were treated at all, you would plot these health insurance rates and you would say, okay, well, what am I supposed to do? Well, there's a lot of simple diff and diffs, a lot of simple kind of 2x2 diff and diffs you could pull out of this picture. You could just forget about those 2019 expanders. What if they didn't exist? What if you didn't even know about them? Then you would be comparing the 2014 switchers to the non-expansion group. And that's the picture that you would get right here. And this is an awesome looking diff and diff picture. Like this is nice, compelling evidence right here. This is good. So your job could be done. But there's more information. So you don't want to throw this stuff away. So you could say, all right, well, what if instead we forgot about the 2014 expanders and you could just compare the 2019 switchers to to the never expanders. And this is fine too. I mean, the idea that this is a valid comparison says, well, neither of these lines had any Medicaid expansion all the way here. For almost the whole plot, they didn't do this policy. And then only in this last year did the green states switch. And so you could do that too. That's also just a simple diff and diff. I think the really tricky thing with staggered timing is that you don't need a group of states that never did the policy. It's a pretty convenient thing to have, but you don't have to have it. One thing you could do is compare, you could be comparing the early switching states. So that's these 2014 guys, they're in the solid black circles. You could compare them to the late switching states if you wanted to. You would just have to forget about that last year when the 2019 expanders actually had the policy. If you just cut that last year off, this is yet one more perfectly fine 2x2 diff and diff. The treatment group is the 2014 switchers. The control group is the 2019 switchers. Pre is before 2014. Post is after 2014, but you don't include 2019. So that would be fine too. You could do this. This is the third now legit diff and diff we could pull out of this picture. But there's one more, and this is the one that causes some problems, and this is the one that regressions do incorporate. You could also, if you wanted to, you could, and regressions do, compare the late switchers. So that was 2019 expansion states. You could compare them to the 2014 expansion states, but you just forget about all the pre-2014 data. And the reason this technically works, I mean, from OLS's point of view, is that yes, those 2014 states are treated. They have their treatment dummies equal to 1, but it's not changing during this time. So if you think that their treatment effect was just a big shift, you can net it out by taking a difference, and that's what would happen here. The treatment group in this particular little comparison would be the 2019 switchers. The control group would be the 2014 switchers, and this could be fine, and OLS thinks it's fine, and I'll tell you that it's not. It's often not fine. It could be, but it's probably not. So that's 4 diff and diffs you can pull out of here, and that's what the main crux of my paper is to say, when you run a regression, OLS is averaging together those 4 types of comparisons. So in this result here, the betas are each of those simple 2x2s, each of those simple things that I just showed you, comparing one group of switchers to another group that doesn't switch in a particular window. Those are the things that you're getting averaged together. Okay, so I think what I liked about this when I sort of stumbled on it and realized this was the answer is that I understand what each of these pieces means. And unlike a typical kind of regression coefficient, I can write each of these pieces in terms of averages of y, which is a thing that I do understand pretty well. So they're being averaged together. The crucial thing is that they're being averaged together using these weights, which I'll just tell you kind of qualitatively. They are classic OLS type of weights. So if you are a group in the data that's bigger, so either the treatment group is bigger, or the control group is bigger, if you're like a pair of cohorts that has a lot of sample size, not surprisingly, you get a lot of weight. And I think we think that's probably how it should be, right? It doesn't have to be how it should be, but at least it makes some a priori sense. The other thing, though, that's a little weird about this is that OLS is really looking for places where it can exploit variation in the right-hand side variables. And what variation in the right-hand side variables means in this context is 2 things. Equally sized treatment and control group. So if you had a little subset, if one of those panels that I showed you had 1 treatment group and 30 controls, that's not a ton of variation because only one of those units has anybody turning on at all. So that's not a lot of variation in treatment. That would get not very much weight. The other thing that variation in treatment means here is treated towards the middle of the panel. So if you're that 2019 group and you only turn on right at the end, that's also not very much variation. And I kind of think of it like in the data set, look at the treatment variable in that pair, the non-switchers versus the 2019 switchers. It's 0 almost everywhere, only until the very, very end do the 2019 guys turn on. That's not a lot of variation. And so the weights here are bigger groups get more weight, pairs that are more equally sized get more weight, and units that are treated closer to the middle of your data set, they get more weight too. And the reason that this is important is because of something that I think I've learned by getting drawn into this literature, but with more with like more formal real econometricians than me that I've really soaked up is you can and should care a lot about what parameter, what number your estimator is actually giving you. And not a lot of people a priori would say like, I really, really want a variance weighted average of these of treatment effects across these cohorts. I mean, maybe you would say that, but I don't think a lot of us would probably say that. And OLS is imposing that on you. It's like shaping your parameter in this potentially weird way. Now, maybe it doesn't matter, but maybe it does really matter. And in a world where we're thinking really hard about heterogeneous effects across groups, that can be a big issue. So I'm going to emphasize here again, kind of what I just said, like you need to think, and you can and should think about what you want from your regressions and from your estimation. And OLS is making a lot of those choices for you. But there are new estimators, like I like the estimator in the paper by Brant Calloway and Pedro Santana. That's a paper where you choose, like you say ahead of time, what average of treatment effects do you want? And that's good. I think people are sometimes like, people get two-way fixed effects estimates that look good. And I think some people can be worried that changing these things can undermine it or make it look bad in some way. But I think this is actually really hopeful. It's like putting this crucial choice in a way like back in your hands and not allowing this regression to pick it for you. And the other thing here that I want to emphasize from this result here is that there's lots of these kind of comparisons. So the way I think about the taxonomy of the types of comparisons that like a two-way fixed effects regression estimator is doing, it's comparing treated to untreated, it's comparing early to late treated, and it's comparing late versus early treated. Are all those valid? No. In general, no, they're probably not. Or at the very least, there are different and sometimes probably not plausible assumptions that you would need for them to all be valid. So now, again, like for me, breaking this thing up into these types of comparisons really, really, really helped me understand what assumptions do I need, what assumptions are more or less plausible, and what can be a problem. So I'll just briefly show you like the plot you could make that from my paper. I don't think that there's a big future for this plot to be like in the main results of anybody's paper. At best, I think this should be like an appendix thing. I look at it sometimes just to see like what's happening, but it was more like pedagogical for me to see how this works and to visualize what's happening with your regression. So what you see in this plot that's produced by a stata command called Bacon decomp is on the y-axis are those betas. So these are just, each circle here is one of those simple 2x2 diff estimates. And this is also for the ACA example. So that's the height of the dots is how big is your diff for this little subgroup. And the x-axis is how much weight do you get. Now, in this particular example, there's a huge non-expansion group and a huge 2014 expansion group. And so it's most ACA regressions, even today, not all, but like most of them, they're pretty much just reflecting 2014 versus non-expansion. That's mainly what they're doing. But you can also plot on here. So these are just the comparisons. You can see the control group and all these dots is the non-expansion group. But you can also plot the early versus late. So each of these X's is a comparison of an early switching cohort to a late switching cohort. And you can look at the dots for the late switching cohorts versus the early switching cohorts. And this is what I'll probably wind up ending on, because these are the dots that are a problem. These X's with the green labels that I just superimposed here. Maybe you notice where they fall on the y-axis compared to the black X's. They're a little lower, and I'll tell you why. And this is the last piece of intuition I wanna convey, which is like, why are these a problem, and why are they a problem for regressions in this context? And maybe hint a little bit at how new stuff kind of fixes this. So the problem basically with those dots is time varying treatment effects. So I'll show you here. So imagine you just had two groups, right? Or pulling out two groups. So imagine like gray line are the 2014 ACA expanders and black line is the 2017 expanders. Let's say that's true. Well, this diff and diff is fine. If you're going to compare the early switchers to the late switchers, you are going to compare the change in outcomes for a group that enters treatment. That's the gray line, but only up to this middle window, right? You're going to compare that change to the change in outcomes for a group that is not treated at all. And so if you believe the typical, the assumptions you need for these types of simple diff and to be valid, that these two groups would have been on parallel trends. Basically, the black line does a good job showing us how outcomes would have changed for the gray line in the absence of treatment. If you believe that, this is okay. The black line's doing a great job acting as a counterfactual for the gray line. The problem is that this second definitive is not fine under this case. So here, this second one, this is kind of related to this is one of the definitives I just showed you, like for the ACA early. This would be comparing this change for the late expansion guys versus the early expansion states. That's going to look at the change in outcomes for the black line right here, and it's going to net out the control group here is the change in outcomes for the gray line. But notice the gray line is not changing only because of just other stuff in the world. It's actually changing because the treatment effect is changing. And so we are saying, oh, well, the comparison for this black line is a huge increase, in insurance rates or something. But that's not what would have happened absent treatment, because that change in insurance rates is happening because of treatment. So that's the real problem. Like, you are going to compare, when you compare to an already treated unit, if the treatment effects are changing over time, then the observed changes in outcomes for a treated unit are being driven by the counterfactual stuff, by the unobservables that you want to control for, plus treatment effects, which you definitely do not want to control for. So this tends to make these kind of comparisons. I would say it tends to make them smaller than the size of the true treatment effect, but it's not just like an attenuation to zero. They can actually flip side. So you could have this is a case where you have positive treatment effects. They're just on a slope. This particular second diff and diff would actually be a negative number. So it would be telling you that that the effect is like to reduce outcomes, even though it is unambiguously to increase them. And so I just want to note here that, like, the average of these dots is a much, much, much smaller number. It's like a little shy of 3 percentage points, whereas the average of the other type of diff and diff comparisons that don't suffer from this problem is closer to 8 percentage points. So that's the last thing I'm going to say here. I just want to wrap up and say, two-way fixed effects is the problem in this case. It's not that staggered timing is a problem. So just like the briefest intro to some of the new estimators is that they are just much more careful about only keeping the good type of comparisons that I just outlined and just explicitly not incorporating those bad ones. They're just not doing the late versus early stuff at all. And they're nice and careful about that. They can deal with your weighting. It's great. Again, like, you can use Bacon decomp to make those scatter plots to see what's going on with your two-way fixed effects if you want, but it doesn't fix them. It doesn't fix anything. It just tells you what's happening. And honestly, at this point, I think if you're in a situation like this, it's probably better to default to some of the newer estimators than to use two-way fixed effects and try to justify it. Because the other stuff is just kind of better in a lot of ways. It's simpler and it gives you a better answer. And so that's it. I have a complex version of the theorem at the end that we don't need to see.
Awesome, Bacon. Thank you so much. Let me ask a few follow-up questions from the chat for everyone's benefit. So one of the first questions, Bacon, is that the Bacon decomp only works when the data set is a balanced panel.
Yeah.
How do you think about an unbalanced panel? Is there any movement towards letting this work? I mean, what happens with an unbalanced panel?
Well, okay, so yeah, no, that's a good question. I mean, from my point of view, it was just a lot more challenging to do the algebra that I did when the panel was unbalanced. But I intuitively, I don't think it's that different, except to say that an unbalanced panel would add problems here. So one way you could think about an unbalanced panel adding problems is, suppose every unit had an exactly constant treatment effect. And so then therefore many of the problems that I'm talking about with that sloped treatment effect line, they wouldn't be there in that case. If you had an unbalanced panel, you could have changes in the composition of those treatment groups over time, because units are in or out, that could make the average treatment effects change over time. And so even if at the individual level, like, everything was a nice constant shift and these were not problems, panel imbalance could make them be problems. I'm sure there's other issues that I haven't been able to deal with there.
Awesome. And let me, Colleen Cunningham also asked a question, which I know you have some work on, which is, what do you do when the treatment is not binary, but maybe it's a level difference or potentially continuous?
Yeah. Okay. That's actually something that I kind of love here, because I just told you this whole story about staggered timing, where the problem was comparing treated units to other treated units. So what I just said was like comparing a later treated unit, later switcher, to an earlier switcher. So then the control group was treated, and the nature of its treatment effects caused a problem. That's the same problem that arises with a continuous treatment, because with a continuous treatment, what OLS is going to do is put a lot of stock in comparisons between like units that have a higher dose versus a lower dose. But there, again, you have a treated control group. And so you really, what you wind up needing in most of, there's a little bit more nuance here, but I'm going to just like kind of skim over it briefly and just give a little warning on the continuous treatment thing and say what you wind up needing for most continuous or non-binary treatment estimators to work is you need a kind of treatment effect homogeneity type assumption. You need those lower dose units to be a good counterfactual for the higher dose units, which means they can't be changing for other reasons. And they have to respond to the lower dose in the same way that the high guys would have responded to the lower dose. So that's like a little bit of a teaser, but I would say that I love it because it's kind of the same type of issue. Like anytime you're comparing, like traditional diff and diff, you're comparing to untreated units. So that's great. You don't need to worry about treatment effect heterogeneity being a problem. Anytime you're comparing treated to treated units, now all of a sudden differences in the treatment effects across the treatment and the control groups can be a problem in addition to the counterfactual stuff that, always could be a problem no matter what.
Awesome. Bacon, do you want to share your paper on that too in the chat?
Oh yeah. I'll put a link in there in a minute.
Okay. And John has put his review of some of these new estimators. There's a lot to think about here. So
yeah.
All right, Bacon's going to stick around. Please do feel free to put more questions in the chat as they come about. Let's turn to John, who's been doing some of the kind of path-breaking work on how to think about parallel trends and the assumptions under which we should believe diff and diff estimators. So John, take it away.
Cool. Can you guys hear and see my screen? Awesome. So thanks, Bacon. That was awesome. That was one of the clearest diff and diff presentations I've ever seen. So I will try and be half as clear as Andrew. And if I can manage that, that'll be a success. So what I want to talk about today, Andrew sort of talked about, we moved beyond the simple 2-period diff and diff model where, treatment happens in the second period. We have treated control, and Andrew talked about, we go on to staggered timing, but he sort of maintained this key assumption in the 2x2 model of parallel trends, that the two groups, if they hadn't gotten treatment, would have had their outcomes on average move in parallel with each other. And so what I want to talk about today is a body of work that I and many collaborators have been working on related to the fact that, well, we might not be sure that these two groups would have moved in parallel. And so what can we do to test to see if that's plausible? And how can we kind of think about sensitivity to possible violations of that assumption? So as Andrew very nicely talked about, the validity of differences depends on this critical parallel trends assumption, which says that if the treatment hadn't occurred, the outcomes for the two groups, the treated group and the comparison group, or in the more complicated staggered setting, the earlier treated and the later treated or the never treated groups would have moved in parallel if the treatment hadn't occurred. But as Bacon nicely highlighted, these groups are often different from each other. They're often, we're typically doing diff and diff because things are not randomly assigned. And so for instance, the early adoption Medicaid states are typically more democratic, typically farther north than the later adoption Medicaid states. And so in practice, we're often not sure ex ante before looking at the data whether the parallel trends assumption holds or not. But one of the things I think is really nice about the difference in differences design, which in part I think has contributed a lot to its popularity, is that there's a very intuitive test for the plausibility of this assumption, which is that if we have more periods before either group was treated, we can look and see, were they moving in parallel before the treatment? Or were there pre-existing differences in trends, often called pre-trends, that sort of show that the two groups weren't moving in parallel before the treatment occurred? And so if they weren't moving in parallel before the treatment occurred, we generally think it's probably implausible that they magically would have started moving in parallel afterwards. Whereas if they were moving in parallel for many years before the treatment occurred, then it's much more plausible that they would have continued to move in parallel after the treatment. And so this pre-trends testing is very intuitive, but a body of recent work has shown that it also has several important limitations. And so what I want to talk to you about today is sort of what are those limitations, first of all, and then what it is that we can do to sort of address these limitations and think a little bit more about, how plausible is the parallel trends assumption and how much would sort of violations of it bias our results. So most of my talk today is going to draw on my forthcoming AR Insights paper, pre-test with caution, event study estimates after testing for parallel trends, as well as my working paper with Ashish Ramachan titled An Honest Approach to Parallel Trends. And in somewhat shameless promotion of my own work, I just wanted to flag that I recently completed this review paper with Pedro Santana, Alyssa Belinsky, and John Poe, titled What's Trending in Difference and Differences, where we go over sort of recent developments in difference and differences, including a lot of the great stuff on staggered treatment timing that Bacon and co-authors have been doing, as well as a lot of the work that I'll talk about today, as well as some other stuff. And we try and sort of show in that paper how all the different pieces of this literature kind of fit together. So we start with like the 2-period model that Bacon nicely went through, and then talk about how different strands of this literature have been relaxing different components of this model. So I hope to give you a flavor of some of this work in the 30 minutes that I have today. But if you're sort of interested in more stuff on recent developments in diff and diff, or how these pieces fit together, we tried to sort of collate the recent findings together in that review paper. Okay. So I'd like to kind of talk about what I think the issues are with this really common and intuitive practice of testing for pre-existing trends. And the first issue I want to talk about is the issue that these pre-trends tests may have low power. And so what I mean by low power is that sometimes there will be a pre-existing trend, but because we have noisy data, we may not be able to statistically say that the pre-trend is different from zero. So I think it's easy to illustrate this with an example, and I just want to highlight that this is one example, but I think that this is a broader phenomenon. And so I'm just going to illustrate it with this example, but I'll later talk a little bit about some more systematic evidence that I've done in some of my own work, where it's not just that I'm picking on this one paper, but I'm using this paper as an example of a problem that's actually fairly widespread. So this is a paper here by He and Wang, and they're interested in studying the impacts of placing college graduates as village officials in China. And so they use an event study approach that compares the treated villages to the untreated villages. In this example, almost all of the treatment happened at exactly the same time. There was like a very small fraction of units that were treated like 1 year after most of the units were treated. But to first order, you can sort of ignore the issues that Bacon was talking about in his talk. And so basically what they do here is they normalize the difference between the treated and the comparison groups in the period before the treatment turned on to zero, right? And so these coefficients to the left of the vertical line correspond with the difference in differences between the two groups prior to the treatment occurring. And then on the right, we have difference in differences between the period before treatment and these periods after the treatment occurred. And so the reason that I chose this paper as an example is they have this quote, which I think nicely summarizes what's kind of the standard approach to testing for violations of pre-existing parallel trends in this literature. So they say the estimated coefficients on the leads of treatment, so they're talking about these 3 pre-trends coefficients to the left here, are statistically indifferent from zero. And so we therefore conclude that the pre-treatment trends in the outcome in both groups of villages are similar. And so villages without the treatment can serve as a suitable control group for villages with the treatment in the treatment period. So they're basically saying we don't find any significant difference in trends in the pre-treatment period. These 3 pre-trends coefficients are not zero. And so that lends credibility to the parallel trends assumption, and we're going to then interpret these 4 post-treatment coefficients as valid estimates of the causal effect. And so if I could put a little bit more kind of statistical structure on the argument that I think he and Wong are making, they're saying we have these estimates here of what the pre-treatment differences in trends are. And we're going to test the hypothesis that they're actually all 0, so that they're actually all equal to these 3 dots. And indeed, if I run a formal F-test of that hypothesis, that these 3 estimated coefficients are actually all equal to these green dots in the population, I get a p-value of 0.81. So by any conventional metric, I can't reject the null hypothesis that in the pre-treatment period, these groups were exactly parallel, which would be good for sort of the plausibility of the parallel trends assumption in the post-treatment period. But the reason that that's not an entirely satisfactory argument is I could also draw these 3 red dots here. And I could test the hypothesis that these 3 estimated coefficients are actually equal to these red dots in the population. And these red dots are drawn such that if I just draw a straight line through the red dots, so I extrapolate this pre-treatment difference in trends to the post-treatment period, I would expect to get means that are actually very close to these estimated coefficients. So while it's true I can't reject that there was no difference in trends in the pre-treatment period, I also can't reject that this treatment group is just increasing linearly relative to the control group in the pre-treatment period following this red line, and that it just continued in this way, and that our estimates in the post-treatment period are basically just picking up on the extrapolation of this trend. I also could draw these 3 blue dots here. And again, I've sort of rigged this example. So if I test the hypothesis that these 3 estimated coefficients are equal to these blue dots, I again get exactly the same p-value, 0.81. So by the same metrics, I can't reject that these pre-treatment coefficients are actually equal to these blue dots. But I rigged those blue dots so that they're on a quadratic curve, so that if I extrapolated the quadratic curve to the post-treatment period, I continued this sort of smooth quadratic trend, I would get a bias in the post-treatment period that's about the same magnitude of the estimated coefficients, but of an opposite sign. So roughly speaking, our coefficients should actually be basically twice as big if this was the true trend, because if I continued it, it would say that this treatment group would have had its outcome decrease relative to the control group. So what I want you to take away from this is that while it's true that we can't reject the hypothesis that the groups had exactly the same trends in the pre-treatment period, we also can't reject the null hypothesis that these groups were on different trends, that if we did some reasonable extrapolation of those trends would produce a bias that would substantially affect the interpretation of our treatment effects coefficients. And depending on how we did that extrapolation exactly, if we did the linear extrapolation, it might mean that our significant coefficients should actually really be 0. If we did this blue quadratic extrapolation, it might mean that actually our coefficients are too small and they should have been much bigger. So this, of course, is just one example from one paper. In my AR Insights paper, I do a systematic review of recent papers published in the AR and AEJ journals, and I do similar types of power calculations and show that this is actually a very widespread phenomenon. So it's very often the case that a difference in trends that we would have relatively low power to detect, say only 50 or 80% power, could produce a bias of a magnitude that's very similar to the estimated treatment effects in the paper. So that's kind of the first issue with the common practice of testing for pre-existing trends. A second issue, which is a bit more subtle, relates to what are called distortions from pre-testing. So what do I mean by that? Well, when parallel trends is violated, just by the noise in our data, we'll sometimes fail to find a significant pre-trend. So as I just showed you, we may have low power to detect certain violations of parallel trends. But the draws of the data where this happened, where we get some noise in the data that masks the underlying trend, are a selected sample from the data generating process. And so if we only analyze our difference in differences analysis when the pre-trends look good, we're introducing a form of selection bias. where we're only analyzing the data in cases where we happen to get noise in the pretreatment period that masks the underlying trend. And so this form of selection bias is what's known as pretest bias. And in some of my work, I've shown that this form of selection bias can introduce additional statistical issues that can often make the bias from differences in trends worse in the cases where we actually analyze it. So let me walk you through a very simple simulation that I think will nicely illustrate the problem here. So consider a 3-period model where treatment occurs in the last period. So this is very similar to one of the examples that Bacon gave, where say everyone who's gonna expand Medicaid gets treated in 2014. So let's ignore the late adopters. We take just the Medicaid adopters in 2014 and the never adopters, right? And so then we might have data in 2012, 2013, 2014. So we have the pre-treatment, 2012, 2013, and 2014. So we have the pre-treatment, and then we have the states that adopt in the last period, 2014, and the states that never adopt. For simplicity, let's think that there's no causal effect of the treatment whatsoever. But in population, the treatment group's mean outcome is on a linear trend relative to the control group. So the treatment group outcome is just growing faster than the control group's outcome in a linear way. And then our realized outcomes are just going to be the mean outcome in the population plus some independent normal noise. So I think this is example that's easiest to see in graphical form. So here on the x-axis, I have something that looks a lot like an event study. So I have -1, 0, and 1. On the y-axis, I have the difference between the mean for the treatment and the control group in each period, right? So in period 0, it's 0. In period -1, it's -3. And in period 1, it's 3. So here, basically, the difference between the treatment and control groups is just growing over time. So the treatment group's outcome is growing faster than the control group's outcome. But of course, if we actually estimate this in data, we don't get exactly the black line because we have some sampling variation in our data. So we get something that looks like one of these gray lines. So I've just simulated this something like 1,000 times, and I've plotted the 1,000 gray lines that we would get for the difference between the treatment and the control group in each of these periods. And so just because of the noise in the data, in some of these cases, we won't detect a significant difference in trends between -1 and 0. So the trend between -1 and 0 just corresponds with the slope of this line, right? Because we're taking the difference in period 0 minus the difference in period 1. So by construction, the cases where we don't find a significant pre-trend are the cases where this slope in the pre-treatment period that's estimated happens to be pretty flat. But how do we get a slope that's pretty flat? Well, the way we sort of flatten out this increasing line is that we get noise that makes this difference at period 0 smaller than its average, right? So if you look at these blue dots here, which are the estimated difference between the treatment and the control group in the period before treatment, we see that they tend to be below the mean in the population, which is at 0, right? And that flattens out this line, so it sort of, that noise masks this pre-trend. But our post-treatment difference in differences estimate is the slope between period 0 and period 1. So you see by kind of a mean reversion effect here, since we have these blue dots here are too low in the pre-treatment period, this slope tends to be very steep for these blue lines in the post-treatment period. So it's easiest to see, I think, if I average this over 1 million draws. So if I average over 1 million draws and I don't condition on the analysis in the pre-treatment period, everything just looks like a line, right? So I see the treatment group is just increasing linearly relative to the control group. But if I restrict to these blue cases where we didn't define a significant pre-trend, on average, there's a small but statistically insignificant slope between period -1 and 0. So the average pre-period difference in differences is only 1.4 in the cases where I don't define a significant pre-trend. But in the post-treatment period, it's actually 3.8. So if we did this on average over all draws, we'd just get 3 in the pre-treatment period and 3 in the post-treatment period. But in the cases where we don't find a significant pre-trend, we're getting a small slope, 1.4 in the pre-treatment period, and we're getting a much larger slope in the post-treatment period. So just because of the noise in the data, in the cases where we're going to say this design looks good, we're getting a picture that looks very convincing. There's a change in slope in the post-treatment period. But in fact, in the true population, there isn't really any break from trend in this data. So kind of to summarize what we've talked about so far, I've kind of talked to you about two limitations of pre-trends testing. So the first is low power. Parallel trends may be violated in the pre-treatment period, but we may not find a significant pre-trend just because of noise in the data. And the second are issues related to pre-testing. So by relying on this pretest as a screen of sort of what's a good design, we're inducing a selection bias known as pretest bias, which can lead us to only analyze the cases where actually we have a very large bias in our treatment effects estimates. There's a third issue, which I haven't talked about yet, but we'll just mention briefly, which is that sometimes we do reject the pre-trends test. So that's good in the sense that we got a signal from the data. Parallel trends is probably implausible. It didn't hold in the pre-treatment period. But there's then a question of what comes next, right? We still want to learn about the treatment of this thing. We still want to write a paper so that we can get tenure. But the standard approach isn't so clear. It basically tells us your design is implausible. And so it's not obvious what we should do next. So you might be wondering, what can we do about these issues? So I'm going to talk briefly about two different types of solutions that I've proposed in some of my work. So the first is kind of a very simple and low cost approach, which is perhaps a little bit less theoretically satisfying as the second approach that I'll talk about. So the first approach is kind of to say, well, we're testing for pre-existing trends. Is that test likely to be powered against, what we think are plausible violations of parallel trends? And if so, like what are the likely distortions from pre-testing based on like the selection bias that I just talked about? So that's kind of the first approach that I'll talk about. And then the second approach is kind of a more formal sensitivity analysis that avoids the need to do the pre-testing, but kind of tries to formalize a lot of the intuitive motivation that's motivating that practice. So let me talk about each of those briefly in turn. So the first thing that I'll talk about are these pre-testing diagnostics to try and figure out, are these issues that I've described about pre-testing likely to be important in the context that I'm thinking about, based on what I sort of view as kind of context relevant economic violations of parallel trends. And so I have an R package and Shiny app that can kind of help you do this. And so the thing I like about this app is it kind of helps you to visualize what I do in my head when I see someone put up an event study plot in a seminar, which is to kind of visually draw a line through the confidence intervals or draw some smooth path through the confidence intervals and say, does it look like I could explain this effect with some sort of smooth trend that goes through all of the confidence intervals? So here I have that same He and Wong event study plot, but I've now sort of superimposed a straight line through that plot with the red squares here, so that you can sort of see that we could really explain all of this pattern with a smooth curve that goes through all of the confidence intervals. And in blue here, what I have is a plot of, if the truth was this red line, on average, if we didn't find a significant pre-trend in the data, what would the coefficients look like? And that's what I have in the blue triangles here. So you can see that if I condition on not having a significant pre-trend, the pre-treatment coefficients tend to be smaller, and the post-treatment coefficients tend to be larger. So overall, I think that this plot sort of nicely highlights what we saw in kind of the drawing on the confidence intervals sort of exercise I did at the beginning, where we can sort of nicely visualize here that we can't distinguish from this event plot whether this group was just on some smooth increasing trend versus there being a break in the trend at the time of the treatment. I want to emphasize that if you see a plot like this, it doesn't necessarily mean that the findings in this paper were wrong. So, if, for instance, we knew that basically the assignment of this treatment was as good as random, or nearly as good as random, we might basically believe that parallel trends holds ex ante. And so the fact that the data is consistent with this smooth trends may not be concerning to us because we know that basically there's no differences in trends at all if the treatment hadn't occurred. So this doesn't necessarily tell us that parallel trends is necessarily violated, but if we're not confident in parallel trends ex ante, it doesn't tell us that they're, that the data is consistent with there having been a difference in trends that looks sort of like this red line that would kind of kill any effect. This package also lets you do some more formal power analyses. So for instance, it reports what's the probability we would detect a significant pre-trend if in fact the truth were that red line. So here that's about 0.33, meaning only a third of the time, if the truth were that red line, would we find a significant pre-trend. We also have some other measures that sort of capture different measures of how likely is the observed data relative under the hypothesized difference in trends relative to under parallel trends. So what I like about this diagnostic approach is that it's very intuitive and easy to visualize, and it helps identify the cases where parallel trends pre-trends testing may be sort of least effective. And another nice thing about it is it requires sort of minimal changes from standard practice, right? So you can run the same specifications that you've been running before, and you can sort of just think a little bit harder and visualize a little bit more what types of violations of parallel trends that you can rule out. What I don't like about this approach and makes it a little bit less theoretically satisfying is that, even if I say I have good power, say I'll detect a relevant violation of parallel trends 90% of the time, well, that means 10% of the time that I won't detect that violation of parallel trends, right? And my confidence intervals are basically assuming that parallel trends holds exactly. The unbiasedness of my coefficients depends on parallel trends holding exactly. So 10% of the time in that case, I'm going to get a biased coefficient, and my confidence intervals aren't going to have the usual guarantees that I want of including the true parameter at least 95% of the time. So we don't get kind of formal statistical guarantees. And then a second issue is that we need to sort of specify the hypothesized trend that we want to compare to. And sometimes there may be a bunch of different possible violations of parallel trends. And it's a little bit hard in this approach to sort of summarize over all these many possible different ways that parallel trends could be violated. And then lastly, sometimes you will detect a significant pre-trend, or you'll say, I can't rule out a meaningful pre-trend, but you still want to publish a paper, you still want to learn something about the treatment effect, so it's not clear exactly what to do in those cases. So in our paper, An Honest Approach to Parallel Trends, we tried to formalize an alternative approach that kind of captures the motivation of pre-trends testing, but doesn't formally require you to test whether pre-trends are exactly zero, and in fact can be valid even if the pre-trends aren't exactly zero. So what we tried to capture in this paper is that the intuition motivating pre-trends testing is that the true pre-trends are informative about the counterfactual post-treatment differences in trends. So if I told you what the true pre-treatment differences in trends is, you would think that would tell you something about how big the violation in parallel trends could be. And so we formalized this by imposing a restriction that says that if I knew the true pre-trends, that would allow me to bound how big the true counterfactual violation of parallel trends is. So it says that the counterfactual difference in trends in the post-treatment period can't be too different from the true pre-trend. And so if we do that, we can obtain bounds on the treatment effect. And we show in the paper how you can get confidence intervals that are sort of uniformly valid, assuming these restrictions on how the pre-trends relate to the post-treatment differences in how the pre-trends relate to the post-treatment differences in trends are satisfied. And so this approach nicely kind of enables sensitivity analysis, where you can say things like, how different would the counterfactual difference in trends have to be from the pre-trends in order to negate a particular conclusion, say a positive effect. So just to give you a bit of a flavor of what these types of restrictions look like. So consider the same 3-period model that I showed you before. So I'm going to denote by delta 1 to be the violation of parallel trends. So what is this? This is the difference in trends between of the untreated potential outcomes between period 1 and period 0 for the treated group relative to the comparison group. So this says, if treatment hadn't occurred, how much different would the treated group's change in outcome have been from the untreated group's change in outcome? Unfortunately, we don't observe the untreated outcomes for the treated group, so we don't know what this bias is directly. We can't learn it from the data, but we do learn sort of the pre-treatment analog of this, which is how different was the trend between period -1 and 0 for the treated group relative to the same trend for the comparison group. And so the key idea in the paper is to say, well, if we knew delta -1, we knew the true population difference in the pre-treatment period, that would be informative about delta 1. So intuitively, we're sort of willing to say that delta 1 is not too different from delta -1 in some sense. So what do we mean by not too different? Well, one way we can impose that is to impose bounds on relative magnitudes. So we could say, for instance, that the magnitude of the post-treatment violation and parallel trends could be no more than the magnitude of the pre-treatment violation and parallel trends. Or we could say that it could be no more than twice as large, which would correspond in this equation with setting this parameter m bar equal to 0. A second type of restriction we can impose would be to say that we can basically smoothly extrapolate this pre-treatment trend to the post-treatment period. So one thing people often do when they're worried about violations of parallel trends is to do a linear extrapolation of the pre-treatment trend. So that would correspond with saying that if I took this true delta -1, I drew a line to period 0, and I continued that, I would get exactly to delta 1. Of course, we may not think that linearity is exactly right. And so we're going to think about these kind of smoothness restrictions that say that this trend is smooth, so it can't deviate too much from the extrapolation of this line. So here I've said that there's some bound m such that if I had the true pre-treatment difference in trends, I could extrapolate that, and I wouldn't be off by more than m as to the true post-treatment difference in trends. So in the last couple minutes I have left, let me show you kind of how you can use this in an example. So I'm going to show you an application to this paper by Benzardi and Carloni, who are interested in the incidence of a cut in the value-added tax on sit-down restaurants in France. So France reduced their VAT on restaurants from about 20% to about 6% in July of 2009. And so Benzardi and Carloni are going to analyze the impact of this change using a difference in differences design, comparing restaurants who were affected by this tax change to a control group of other market services firms whose tax didn't change. And so they're going to do basically a pretty vanilla difference in differences between these two groups of firms. And their main outcome of interest is the impact of this reform on the profits of these firms. So here is the kind of event study plot for this outcome of log profits. And so what you see here is that if you look at the pre-trends, things look pretty good between 2004 and 2006. But in 2007, you get a significant pre-treatment coefficient. So between 2006 and 2007 and 2007 and 2008, things weren't kind of exactly parallel. On the other hand, if you just kind of look visually at this plot, it looks like the change after the reform seems to be larger in magnitude than kind of these dots that are bouncing around fairly close to 0 in the pre-treatment period. So this is a case where we kind of do reject formally that the trends were exactly 0 in the pre-treatment period, but just kind of visually, we do seem to see a break in the post-treatment period. And so we can kind of formalize this intuition with the sensitivity analysis we have in this paper. So here we're doing a sensitivity analysis for the effect in the first year after the reform. And in blue, I have the usual confidence interval from OLS that assumes that parallel trends holds exactly. And then what I have in red here are our robust confidence intervals under the assumption that the post-treatment violation and parallel trends is no more than this factor m bar times the maximal violation and parallel trends in the pre-treatment period. So when m bar is 1, which is sort of this second red interval here, I'm saying there can be a violation in parallel trends, but it could be no larger than the true maximum violation in parallel trends in the pre-treatment period. And so if I do that, my confidence interval is of course wider than when I assumed that parallel trends held exactly. And that's for two reasons. The first is that this pre-trends coefficient is actually not zero. We can reject that it's zero statistically, right? And so there's likely some bias, but we're also uncertain about how big this difference actually is, right? So this difference could be, 0.05, but it could also be 0.01. So this confidence interval here is sort of taking into account the fact that we have some statistical estimate of how big that pre-treatment difference is, but we don't know exactly how big it is. But even so, if we bound the post-treatment violation in parallel trends by the maximal pre-treatment violation in parallel trends, we still get a significant effect here. So we can still rule out the null hypothesis that there's no effect of this tax change on profits. Of course, if we allow the violation of parallel trends in the post-treatment period to be larger than the maximal violation in the pre-treatment period, then eventually we won't be able to rule out a zero effect. And in this example, that kind of breakdown happens when we set M bar to be about 2, meaning that we allow for the post-treatment violation in parallel trends to be about twice as large as the maximal pre-treatment violation in parallel trends. So we can say in this case that this effect is robust to allowing for violations that are about twice as big as the largest one that we saw in the pre-treatment period. Now, in this particular example, it turns out that the post-treatment period corresponds with the post sort of Great Recession period. So if we think that like restaurants and other industries are affected sort of differently by macroeconomic shocks, it may actually be plausible that in 2009, the effect was twice as large as in any pre-treatment period, because we're talking about like the biggest recession that we've seen in sort of a long point. But I think that this sort of sensitivity analysis kind of gives us a language for talking about how bad would the differential shocks to restaurants have to be in the Great Recession relative to what happened previously in order for us to believe this effect. So just to kind of wrap up what I talked about today, I think tests of pre-trends are kind of a very intuitive test of the plausibility of the parallel trends assumption, but they don't solve all our problems. And in particular, there are these issues that they may not be powered to detect the violations of parallel trends that we care about. And if we kind of screen on these pre-trends, we may be introducing a selection bias known as pretest bias. And so what I talked to you about today is some tools that can be used to kind of diagnose how bad this problem may be and to perform sensitivity analysis to how robust are our findings to plausible magnitudes of violations of parallel trends. The last thing I want to add is that I think, I've talked to you today about a lot about statistical tools, but I think these statistical tools interact really nicely with people bringing economic intuition to bear to the problem. And so I think in addition to just statistically testing for parallel trends or statistically doing these sensitivity analysis, I'd encourage people to sort of bring in economic knowledge about, why we think these groups are likely to be parallel and what economic factors might lead them to not be parallel if parallel trends is violated and what those violations of parallel trends may look like. I think kind of combining that context-specific knowledge with these new tools for diagnostics and sensitivity will sort of give the best and most credible finished product in diff and diff designs. So thanks very much.
John, both you and Bacon just laid that out so clearly. So thank you so much for helping us all understand these issues. I have a few questions that I'd like to raise just to follow up, and then if others have questions, please put them in the chat here. And I want to begin by intersecting the two presentations. So Bacon talked about how in staggered designs, 2A fixed effects models, we get bias when there are, for example, heterogeneous treatment effects over time. And that comes about because OLS will innately give some weight to a comparison of the later treated units versus the earlier treated units. And so my first question is for maybe for both of you is what happens to the pre-trends when you run that kind of analysis? So is it possible that the bias that comes about that Bacon talked about, it shows up in the pre-trends, or is it possible that the pre-trends appear parallel when in fact they're not? How do we think about pre-trend testing in staggered rollout designs? So I'll just open that up to whoever wants to jump in.
Go ahead, Bacon.
I just want to say that they're there. I mean, they don't go away. And I now just think of two-way fixed effects estimator in this case as just a particular way to average a particular set of comparisons. So it's not going to get rid of anything. It could mask things by averaging them in a weird way because of the weights. It could mask things by averaging them in a weird way because some of the comparisons, the pre-period is going to contain treated units. That can be weird too. And so I think the things, when I think about this question of like, well, how should I consider pre-trends, or what do pre-trends mean? I always like to still kind of break it down to those simpler estimators where parallel trends or pre-trends is more well-defined. And so, yeah, I think they're still there. And I think one thing that's good about new estimators for staggered timing is that they're clearer about what's being averaged and what pre means. So for example, I'll say what I mean by what pre means or what pre-trends mean. Like in everything I talked about, when you compare to an already treated unit, there could be some bias that comes from the fact that treatment effects are changing over time. But pre-trends or the traditional parallel trends assumption is all about like untreated potential outcomes. So that doesn't have anything to do with treatment effects. So it's like now there's sort of two types of bias. And so when we talk about pre-trends, now like with two-way fixed effects, the situation has gotten a little bit more complicated. We're kind of mixing together two things that can both be problems, but like they're defined a little differently. So I just want to say, like, I'm happy to talk about, give my like 2 cents on new estimators, but essentially they're going to average things together in a clearer way so that and that puts us on much stronger footing to answer questions like you're saying, like, how should I think about pre-trends? Well, two-way fixed effects muddies the waters for lots of reasons. And new estimators make that question a lot clearer to answer, and I think make it more amenable to a lot of the tools that John's developed and was just talking about.
Yes, I think that was a great answer. Let me just add a little bit to it. So there's this great paper by Sun and Abraham that thinks about this issue. So Bacon in his presentation talked about kind of the simplest two-way fixed effect specification you could run, where you just have a post-treatment indicator, right? So it's just 1 if you've been treated and 0 otherwise. The common thing to do with two-way fixed effects estimators to get kind of an event study plot is, rather than just having a post-treatment indicator, you have indicators for like time relative to treatment. So like you have like one indicator that turns on if you're like 1 period after treatment, and one that turns on if you're 2 periods after treatment. And then you do the same thing if you're like 1 period before treatment and 2 periods before treatment, and so on. And so you use those sort of before treatment indicators as kind of the things that you use to test for pre-trends, like in those plots that I showed you. But Sun and Abraham show that, similar to the kind of weird weighting issues that Bacon was talking about, those event study coefficients also have weird weighting issues, so that you would hope that the -1 coefficient is comparing like trends for people period before treatments to people who, like, the trends for people period before treatment to the trends for people who aren't yet treated at the same point in time. But it turns out that that's not true. So that like -1 coefficient actually has some weights on people who are like 5 periods after treatment. If there's no heterogeneity in kind of the path of treatment relative to the timing of treatment, those weights kind of wash out. But when there are these heterogeneous treatment effects, you can kind of have your pre-trends estimates be affected by the heterogeneity of treatment effects after treatment occurs. And so this kind of can go both ways. It can mean that your pre-trends can be non-zero, even if parallel trends is true. But it also means that your pre-trends, and when I say pre-trends, I really should mean estimated pre-trends. Your estimated pre-trends can also be like 0, but that's because like somehow the heterogeneity canceled out the pre-existing difference in trends. But the good news of that is that like the problem is just the estimator. The problem is not like some fundamental like identification challenge in the data. And so like these new estimators like Callaway and Santana or like Borisiak et al. And so on, basically what they're doing is they're being very explicit about who's being compared to who at each period of time. And so basically the way that they construct pre-trends estimates is something like, I take all the units who are a period before treatment. I take all the units who are not yet treated at that point, or, you know, at like I take units who are treated later, and then I just do a diff and diff between those in the period before the treatment. So I have like, you know, to make it concrete, like say I have a group of units who are treated in 2014. So I look at the trends between 2012 and 2013 for those units. I compare that to the trends between 2012 and 2013 for some units who were, say, never treated or treated, you know, much later than 2014. And so in that way, I can sort of do placebo estimates before treatment occurred in a way that is sort of, I know who I'm comparing in all of those periods. And the nice thing is that the tools that I talked about today sort of work really nicely with those types of estimates as well. So for instance, like Pedro Santana has on his website for the like DID package, which is like one of these new tools, has like a how-to guide on how you can use that to sort of create an event study that plugs really nicely into the packages that I talked about today. So I guess I would echo what Bacon was saying, that like, I think the takeaway I see from this new staggered timing literature is not that staggered timing is like a problem from an identification perspective, but you want to be really transparent and explicit about who you're comparing at which points in time. And there have been a lot of different ways of sort of making that precise, but you know, they're all basically just trying to be very transparent and explicit about who we're comparing at which points in time so that we have sort of sensible and clean comparisons.
I think that's so helpful, John. I mean, so for me, one of the takeaways is if you don't have parallel, if you just run straight OLS to a fixed effects model, you don't have parallel trends. Actually, that could be fine because you're just picking up part of the wrong comparisons, and maybe once you use some of these new estimators, it could actually fix your problem. Let me ask a follow-up question then, which I'm not sure you're going to like this question, but I need to ask it. There's been obviously an explosion of work done to try to parse out the good comparisons from the bad comparisons. There's the Son and Abraham method. There's just kind of a stacked regression where you just throw out the later treated states and just stack your data so that you only have clean comparisons. There is the Gardner method. There's gosh, I'm missing a whole. There's the Pedro Santana and Callaway method. There's a whole ton. The Carell and Borisiak is like all these new approaches, right? So you know, my understanding of what's going to happen is that the one that's easiest to implement is probably going to win, whether that's the cleanest R stated package. But I want to give you guys a chance to weigh in on what you think the best estimators are for people to adopt, and any justification for why you think that is, or and you don't need to to say anything bad about the other papers, but just from a practical perspective, what should people do, right? So I'll send that just out to both of you guys.
I think the good thing is that many of those new estimators are really similar and doing really, really similar things. I guess if I think of like the history of these new estimators, like when we started to realize some of the problems with using two-way fixed effects and the way that heterogeneous treatment effects can break it, people wanted to know how to fix that problem. And so some of the estimators, like they fix that. They're like, we avoid that problem. And that's fine. There's a lot of ways to do that. So like you look at Cengiz et al., like their paper, the QJE paper on minimum wage changes, or Deshpande and Lee have a really nice paper on Social Security office closures. Those are like early stacked diff and diff solutions that were kind of like, they kind of arose from practitioners early, and it's like you change the structure of your data. So you only really are making sure that you ever compare groups of units whose treatment turns on to groups of units whose treatment is off. So that's good. But that avoids those problems. But there are some questions about like, well, if you do that for a bunch of different treatment cohorts, How are they getting weighted together? That's not totally clear. So some of the estimators basically took one step to solve the bad comparisons problem. But others like Callaway and Santana, they also solve the bad comparisons problem, but they let you be way more flexible with what kind of weighting strategy you want to use. But you could do a stack diff and diff that gives you the exact same numbers as Callaway and Santana. That you could make them be the same if you wanted. So in practice, there are going to be like these little differences that give you like a number here that's not quite the same as a number here. But I think we're getting to a point where the new approaches, they're doing similar enough stuff that it will be, I think it'll eventually be possible to like make them all, maybe not all. The ones I'm most familiar with, you can probably make them all the same. And I think in practice, we'll hopefully get to a point where people aren't having to pick one or the other, because we'll realize like, oh, well, I do this and I implemented it with Callaway and Santana's code, or I implemented it with a stack thing. I think that'll happen. Now, I'm not speaking to like the Gardner or Borussia, Jarval, and Spice papers, which are like all about imputing counterfactual, imputing untreated outcomes. So those have a similar, they're addressing similar problems, but they're doing it in a little teeny bit different way. So I could imagine that those methods would like give you a slightly different answer. But with respect to like what should you do, it does seem like maybe we're in like a confusing space where it seems like there's a lot of options and they might give slightly different answers. But I guess the message I'm trying to say is they're really not nearly as different as they seem.
Yeah, I agree with what Bacon said. I mean, I think, the emphasis of this recent literature has been on being very explicit about who the comparison group is and making sure that that comparison group is sort of a sensible, clean comparison group. And so the methods differ a little bit in like, what is that comparison group? Is it the last to be treated? Is it the never treated? Is it the not yet treated? And so those choices can matter on the margin, but like, with a lot of stuff we do, there's kind of some researcher degrees of freedom. Like, how did you select your control group? Was it matched from, all the states? Was it matched from states in the same region? Was it, so like this feels to me like another one of these things of like, we often make a lot of choices about like who's the comparison group. And so this is another choice you can make as to like how we define that comparison group. And in some contexts, one might be more plausible than others. So like in some cases you might say like, never treated are not very good controls, but like the exact year that you got the treatment might be a lot better. And so, using not yet treated is better than never treated. So I think that they're like, these differences in general are small, but there often can be sort of researcher informed choices of those types of parameters. I guess practically my experience is that in most situations, like if you do Callaway and Santana, or you do Sun and Abraham, or you do like Borisiak et al., like it's not going to make a big difference in most settings that I've seen. To be honest, a lot of the time those things come out similar to two-way fixed effects. Like the treatment effect heterogeneity is often not that large, such that like two-way fixed effects comes out very different either. But I mean, I think to me, the benefit is not just that like you're robust to treatment effect heterogeneity, but you actually know who you're comparing. I mean, to me, like one of the biggest issues with two-way fixed effects is not so much that it's like biased under treatment effect heterogeneity, although that's obviously concerning, but just that like, I have an estimate in a table, but I can't actually tell you whose outcome it's comparing to whom. And that for me is just kind of like a concerning feature of doing research when I have a table and I don't know what the estimates in the table actually come from. I guess in terms of the like Borusiak and Gardner stuff versus the Callaway and Santana stuff, I think there are subtle trade-offs. We talk a little bit about this in my review paper. Essentially, what I see as the main differences are, like the Callaway and Santana paper starts out by basically saying we're going to do very simple diff and diffs for units that were treated at each point in time, and then we're going to aggregate those up with certain weights that are informed by what we're interested in. And they mainly use one pre-treatment period for each treatment cohort. So if you're first treated in 2014, the sort of pre-treatment data we use for you is 2013. And so that's very transparent, but it is throwing out a little bit of information, because if we have data going back to 2010, then we're not using the data on 2010, 2011, and 2012. And so some of these newer estimators are trying to use some of that earlier information as well. So rather than basically treating the pretreatment period as 2013 for those units, we'll treat it as like the average of 2010 through 2013. And so that can add some precision gains because you're averaging over more periods. On the other hand, like based on some of the stuff I talked about today, like if these two groups are diverging over time, then like you're gonna have more bias if you put more weight on earlier pretreatment periods because like they've had more time to diverge between 2010 and 2014 as opposed to like 2013 and 2014. And so I think there are kind of subtle trade-offs between like maybe you get a little bit more precision, but you're also putting more weight on earlier periods. They may not be like as good at controls or as good for parallel trends. So I think, unfortunately, you know, since I know I'm talking mainly to practitioners, I think it's not like there's a great standard practice of like the literature has converged on this. If you're looking for someone to blame for why you chose what you chose, you know, we have in our review paper some discussion about when you should choose one over the other. So, you know, if you want to blame me for your choices for your referees, I think we can both make out ahead with that. But I think this literature is you know still a bit open. There's subtleties that kind of determine when one method is better than the other. But my overall impression is that like kind of in most cases, these subtleties don't make a huge difference. And I guess my takeaway for applied researchers would be like sort of make sure you're doing something that has a sensible comparison group in your setting. And like if you can justify the comparison group you're using, the exact implementation method is probably not going to matter that much. And so, you know, you can sort of, I think, just run with one of these things. And there are also nicely some packages that have been developed now that'll plot like 6 of them at once. So, you know, like Appendix J can basically be like, you know, I tried Callaway and Santana. I also tried these other 5 things. And, you know, there will be cases where those give different answers, but I think in like a general rule will be that like that Appendix J will likely sort of support the same conclusion as whichever of them you chose as your main thing.
Yeah, this actually I want to just say like one little last pithy thing that I wound up like writing an email to someone the other day, but some John said reminded me of it. I think the really good thing about these new estimators being clearer about comparison groups is that it allows us to use our context knowledge and our economic knowledge to navigate the econometrics better. And then the econometrics create a much more specific and useful role for that context knowledge. So I view those things, they're much more complementary now than they were under the two-way fixed effects world because they can help each other.
This is so great. And I've learned that we are about over time, but I do want to ask one more question. So people can feel like they need to leave, but I need to ask John at least one question about his work. So, you know, one of the hallmarks of the diff and diff literature is that it can be challenging to figure out what to do with the standard errors. You know, I think about Duflo, Bertrand, Mullin-Nathan, and thinking about the clustering at the state level when state is the group, you know, that treatment is assigned at. And there's been kind of you know, a whirlwind of like, what do you do with your standard errors, particularly in diff and diff designs? And all of your work on pre-testing depends on sort of getting the standard errors right. And so I'm curious how you think, and of course you've got issues when you have a small number of clusters, maybe just one state has adopted your policy. So I'm just curious, how do you interact? Thank you so much, Bacon. How do you think about that? You know, the literature on what do you do with your standard errors, clustering them? How does that intersect with your work on pre-trends? And in particular, like, what is there anything that we should do or take away from the intersection of those two pieces?
Yeah, good question. So first of all, yeah, you're totally right. I mean, we've focused on robust inference to make your inference robust to violations of parallel trends. Kind of the baseline inference has to be correct under the assumption of parallel trends, right? So like we're sort of relying on you having gotten the standard errors for those betas, right? And choosing how exactly you cluster those standard errors can often be a bit confusing. I would say that they're kind of two approaches to clustering in the literature. There's this kind of the canonical view is kind of what's called the model-based view, where you think about, are the errors correlated across different units, and you kind of want to cluster at the level of the units where the errors are not correlated. That's the traditional view, but it can kind of be confusing. There's this great 2017 paper by Abadi, Athey, Imbens, and Wooldridge, where they kind of talk about, well, if you think like, outcomes are correlated across people with, similar characteristics, then like why in an RCT do you not need a cluster by, say, gender? Because people with similar genders, have similar outcomes. And so they take what's called more of a design-based approach to clustering, where they sort of think of the need for clustering as mainly arising from correlation of treatment status. So like if treatment status is determined at a state level, then if, Evan and I are in the same state, then we're gonna always have the same treatment status. And so at least in like RCT land, they kind of advocate for clustering at the level at which treatment is assigned, or at least where treatment is correlated. So treatment could be correlated at levels where it's not perfectly co-determined, if like, it's either the case that the states in the Northeast tend to all get treated, or the states in the Northwest tend to all get treated, but sort of not both. But so their view is basically you want to cluster at levels where like sort of the treatment assignment is correlated. Their paper doesn't explicitly talk about diff and diff, but I have this paper with Ashish Rambachan on design-based uncertainty for quasi-experiments that sort of tries to make these same types of ideas for diff and diff. And so from that view, I think the best rule of thumb is sort of, I think for most cases, you want to cluster at the level where the sort of, at least at the level where treatment is assigned, and possibly, like if you were thinking about something like hurricane shocks, you might want to cluster at a level of like places that are, tend to be affected by the same hurricanes or something like that. There's some discussion of this in the design-based uncertainty paper, and also probably a slightly more extended discussion of this in my review paper. So yeah, choosing the level of clustering is a challenging issue. And there are definitely econometricians who kind of are holding on to the model-based view of it, and that can definitely make sense in some contexts. But I generally tend to be more sympathetic to the design-based view, where you kind of view treatment assignment as sort of the thing that's generating the need for clustering. And I think that approach sort of gives at least somewhat cleaner practical recommendations.
Awesome. Thanks so much, John. Thanks again to Tomas for organizing and letting me put together this panel. And thanks so much to John and Bacon for just super clear presentations. They will save us all from ourselves in the future. So let's give them all a silent round of applause here. And thanks all for joining us. I hope you all have a fantastic day.
Thanks for organizing, Evan.
Thank you, Evan.
Thank you all.